Talking this whole time about derivatives, right? And now we're going to do antiderivatives. So you can think of antiderivatives like you would when you learn multiplication and then you learn division, right? So multiplication takes you to a product, division takes you back to your original factors, pretty much. And so derivatives take you to the new function, the derivative. Antiderivatives take you from the derivative to the original function, all right? So you're working backwards. Function f is an antiderivative of f on an interval I if f prime x equals f of x for all x in I. You'll notice they have a capital letter there, which is your derivative there. If f is an antiderivative of f on an interval I, then g is an antiderivative of f on the interval g. I, if and only if g is in the form g of x equals f of x plus c for all x in I, where c is a constant. There we go. So let's talk about what this means. When you do antiderivatives, you have to consider the fact that there might have been a constant in your original function. What happens to constants when you take the derivative of them? They zeros out. And so when you take the antiderivative, you have to consider the constant could be there, right? There could have been a constant. And so that C just represents the constant that could have been, all right? They give you some terminology at the top of page 243. If you look at the top of page 243, the C is called the constant of integration. The general derivative is the derivative that has the C in it, and the general solution is the function plus C of the differential equation. Let's look at this example. Find the general solution of the differential equation y prime equals 2. Y prime equals 2. All right? And so if y prime equals 2, that means y prime, that is the derivative. So the derivative of this function is 2, all right? How then do we get a derivative that is just a constant? What must it have been prior to that before taking? It must have been 2x. So y must have been 2x, but there could have been a constant attached to it. And so you have to consider that constant when you do your antiderivative. They show you why this is true. All right, if just think about your linear equations and what you know about them. This particular one has y equals 2x. The slope is 2 plus 2. The y-intercept is 2. This guy right here is just y equals 2x plus 0 because the y-intercept is 0, right? And this one is y equals 2x minus 1 because the y-intercept is negative 1. So we have those three functions shown right there. Y equals 2x plus 2, y equals 2x, and y equals 2x minus 1. Let's take those derivatives. All right, what's the derivative of the first one? Y prime is 2. What's the derivative of the second one? 2. And the third one? 2. There we go. So when you're given just the derivative with no other information, you must add this plus c to indicate you are aware that it represents any function that starts with 2x plus any number. Because any function that is 2x plus any number will give you a derivative of 2. 43, I want you to look at all the notation. All right, when solving a differential equation in the form dy dx equals f of x, it is convenient to write it in the equivalent differential form dy equals f of x dx. All right? So if I were to have some function and take the derivative, dy dx, derivative of y with respect to x, typically you will write it when you're talking about antiderivatives with that dx over on the side of the f of x, right? And so then we create this antiderivative type situation here. And that's kind of dark. We'll zoom in a little. So then if I am solving this particular one, I have this little guy right here. That tells me I am actually going to be taking the antiderivative. This is my integrand. This is what I'm taking the derivative of. Variable of integration, that's the variable I am considering. All right, this will then be my original function, and this will be my constant of integration once I have taken it. All right, so this symbol right here, which reminds me of music symbols for those of you that play instruments, that is your integration symbol right there. That indicates you are finding the antiderivative, okay? So if you just had something written like that, that would be like telling you to find the antiderivative, right? Just like a plus or minus sign tells you to add or subtract. All right, so look at how it's read. The expression with little integration symbol here is read as the antiderivative of f with respect to x. So we have that term with respect to x. It is important that you know what variable you are taking the integration with, because there will be times when we do change the variables. So with respect to x, so the differential dx serves to identify x as the variable of integration. The term indefinite integration is a synonym for antiderivative. Indefinite integral is antiderivative. So indefinite integral, we will get to definite integrals as well. But the term integral is antiderivative, all right? So those will be used interchangeably, all right? If it says find the integral, and it gives you some function, they're saying find the antiderivative, okay? Indefinite, we have the C. Definite, we actually know what the numbers are. So we'll do indefinite right now. But I want you to pay attention. The derivative of a constant is 0, right? So then the antiderivative of 0 is a constant, right? They're just showing you how it pairs up. The derivative of some constant times x is just the constant. So the antiderivative of a constant is just that constant times x plus c. It's just back and forth. The derivative of some number times a function is just that number times the derivative of a function. Same thing works. When you take the integral of a function that just has a number in front, you can yank that guy out and do the integral first, and then multiply it by the constant that was there to begin with. The differentiation of two functions added together is just the differentiation of each one added. So the integration of two functions can be separated by the integration of each of the functions individually. X to a power, let's look at this one, because this is where we kind of go backwards here. If I am taking the derivative of x to an n power, my first step is to multiply by the n, and then my new exponent is n minus 1, okay? When you take the antiderivative of x to an n, your first step is to add 1 to your exponent, and then you divide by your new exponent. So instead of multiplying and subtracting, those are your steps, right? You add and then divide. So it's literally like you're doing the inverse functions. That's what they are. They're inverse functions of each other, right? So just like in algebra, when you did order of operations, you did it one way, but when you were solving an equation, you did the other, right? So in order of operations, you would do multiplication, division, then addition, subtraction, right? When you solve an equation, you actually do the addition, subtraction, and then the multiplication and division, right, when you're solving. And so this is the same concept here. So instead of multiplying and subtracting, you're going to add 1 and then divide. And of course, we still have the C. Trig functions. If the derivative of sine is cosine, then the antiderivative of cosine is sine, right? Derivative of cosine is negative sine, then the antiderivative of sine is negative cosine. It flips it. Derivative of tangent is secant squared. Well, the antiderivative of secant squared then is tangent. These are all ones you should already know. Secant goes to secant tangent, then secant tangent goes to secant. And so all of this follows. It's just showing you if you go, just like multiplication division, if you go one way to get to the answer, then from the answer you go the opposite way. Okay? And so that's what we're about to do with integration. We're working back towards the original function from the derivative. All right? Applying these basic rules. Let's look at example 2. Describe the antiderivatives. I want to pay attention to this word. You'll notice that it is plural of 3x. Well, my rule says that I can just ignore the 3 and I can take the antiderivative of x, and then the 3 just goes in front, all right? So I have the antiderivative of 3x. So then what is my exponent on my x? What's my exponent here? 1. So my rule is I add, right? So I now have x to the 1 plus 1, right? All over the 1 plus 1, dividing by my new exponent. So I say it's going to be 3x to the second power all over 2. Another way to write that would be 3/2 x squared. And then I must consider my c as well. If you remember, when you take the derivative, you have dy dx. And so when you're writing your integrals, so when you take this derivative, he actually goes away because he was part of the antiderivative. All right, this is just telling you what variable you're taking that with respect to. So let's look at these. So just like in differentiation, there are times when you want to rewrite before you do anything. So we have been given this original integral here, 1 over x cubed. So what I'm going to do with that is I'm going to rewrite that with a negative exponent. So I'm going to rewrite that as the antiderivative of x to the negative 3. And so now I'm going to take that negative 3 and I'm going to add 1. What is negative 3 plus 1? Negative 2. And so we see I now have x to the negative 2 over, because I'm dividing by that new exponent, negative 2. And so I'm not going to leave it like this because this is not a pretty way to write it, right? I'm going to rewrite it as negative. There's where my negative, so my negative 2 pulls a negative out of my fraction. And now in the denominator, I still have my 2, and I've moved my x squared to the denominator so that I don't leave it as a negative exponent. And of course, I have my plus c. So I have 1 over negative 2x squared plus c. All right. Look at the next type. So for the next type, I have a radical. Radicals are something else you want to rewrite. You can rewrite a radical as a fractional exponent. Square root is the same thing as 1/2. Remember, your exponent is your numerator and your index of your radical is your denominator. If your radical doesn't have an index, it's always 2. Okay, so square root of x is the same thing as x to the 1/2. Well, I'm going to add 1/2 plus 1. What is 1/2 plus 1? That's 3/2. And then I'm going to divide by 3/2. By the way, dividing by a fraction is keep, change, flip. So when I correct that and make that a little prettier, I'm going to get 2/3 times x to the 3/2 plus c. All right, the last one they did was a trig. You don't necessarily have to rewrite these trigs like this. As you get more used to it, you won't. But what they did is they pulled that 2 out so you could concentrate just on the sine x. Now, antiderivative of sine is going to change positive negatives, okay? Because remember, I'm going back towards the cosine, and the derivative of the cosine actually flip-flopped my positive negative, right? So antiderivative of sine is going to be negative cosine. And I leave that 2 out here, right? Negative cosine is all I have to worry about. And then, of course, I'm going to simplify these with negative 2 cosine of x plus c. All right, negative 2 cosine of x plus c. All right. You have a radical. You want to rewrite it to the integral of x to the 1/3 dx. When you take the derivative, you're going to add 1. So you're going to have x, they didn't give me enough room, to the 4/3 divided by 4/3 plus c. When you divide by, I'm going to write down here because it's not easy to see. When you divide by a fraction, it flips. So 3/4 x to the 4/3 plus c. Different ways. So you have polynomials, which means you can have multiple things within it. And so they've shown you how to break it up. So the first one's easy. We have just a dx. Well, there's nothing there. So remember, if there's nothing there, you were actually multiplying by a 1, right? And so if I were going to take the derivative of that, the derivative of a constant, the antiderivative of a constant is just that constant times x. So 1 times x and then plus c. All right? Then I get to like a binomial. All right? I have a binomial here, x plus 2. You will not, I promise you will not going forward actually break it up like this every time. We're about to do one where you don't, okay? But just to show you that it can happen, you could take the integral of x and the integral of 2 and add them. Well, the integral of x, what's my exponent here on x? 1. So I'm going to say x to the 2 divided by 2, right? Plus, what's the integral of a constant? The constant times x, right? Plus c. And you can rewrite that 1/2, not 1x, 1/2 x squared plus 2x plus c, right? That works. Okay. Now let's look at the third one. We have 3x to the fourth minus 5x squared plus x. You could break it up into three integrals if you want to, or you can just take the integration individually. So look at 3x to the fourth. It's going to be 3 times x to what power? Add 1, right? To the fifth, divided by 5. Minus 5x to the what power? 3 divided by 3. Plus x to the what power? Second power, divided by 2, plus c. And so I would say that's 3/5 x to the fifth minus 5/3 x cubed plus 1/2 x squared plus c. Does that make sense? Beautiful. So when I have x plus 1 over the square root of x, I will want to rewrite it in this fashion. I will want to put each piece of the numerator over the denominator and see if I can reduce it that way before I start doing integration. There will come a time when we can do integration that will not reduce, but that's integration by parts, so we're not quite there yet. In this case, you wouldn't need to. You wouldn't even need to do that process because you can simplify these first. What you do need to consider is that you have to consider your properties of exponents. So I have x over x to the 1/2 plus 1 over x to the 1/2, right? And so my properties of exponents say this has an exponent of 1. When I am dividing like variables, I subtract their exponents, right? So for this first one here, I have x to the first over x to the 1/2. I just subtract those, right? 1 minus 1/2. Does that make sense? And so this becomes x to the 1/2 plus I have something in the denominator. How do I write an exponent that's in the denominator? X to the what? Negative 1/2. And so now I actually have something that I can deal with just my properties here that I've already learned. Think about it this way. You'll be able to do this one. X cubed over x squared is what? X to the 3 minus 2, actually, which is x to the 1, which is x. You did properties of exponents there. Okay. So this is x to the 1 minus 1/2.
Are we trying to prove that the second side is equal to the left?
No. That was just the rewriting of it. They just rewrote it. So this is the first step. You just take the first piece of the numerator over the denominator plus the second piece of the numerator over the denominator. That's your first step to doing this. That's your rewrite process. And then I rewrote it again. So instead of writing square root, I wrote 1/2, x to the 1/2. And then I just reduced properties of exponents. 1 minus 1/2 is 1/2. When it's in the denominator, it's to the negative exponent. So that's all I've done so far. I haven't actually taken the integration yet at all. So now to do my integration, I am actually going to take this and I'm going to say, well, I'm going to take 1/2 plus 1, right? Which is what? X to the what? 1/2 plus 1 is 3/2. If I divide by 3/2, it's like multiplying by 2/3, right? Plus, what is negative 1/2 plus 1? X to the what? 1/2. If I divide by 1/2, it's like multiplying by 2 plus c. You may leave it like that. If you are going on to plugging something in and solving, you may want to write it as a radical because something to a radical makes more sense than something to a fractional exponent. But if you are just doing the antiderivative, you can leave it like that. You will not want to leave a derivative with negative exponents. That's not mathematically correct, but you can leave it as a fractional exponent. That's fine. right, so to integrate this, I have to take this exponent and I have to add 1. So to get a common denominator, to add 1 would be plus 2 halves, right? Which gives me the 5 halves. And then if I'm dividing by 5 halves, I'm actually multiplying by 2/5. So then I would add this. I would add 2 halves to this. I would get 3 halves. When I divide by that 3 halves, it's actually multiplying by 2/3. Keep, change, flip. Same thing here. Negative 1/2 plus 2 halves gives me a positive 1/2. Then I divide by that, which is the same thing as multiplying by the 2.
Yeah,
All right. So trig functions, they're really not any more difficult. You have to basically memorize your derivatives and antiderivatives, which if you've memorized your derivatives, you really know your antiderivatives. But in this case, we have sine over cosine squared. And we want to rewrite this. We don't have an antiderivative for cosine squared. And we will get to substitution, but that's not something we actually need to do with this one. For this one, I can just say, well, I can break it up into 1 over cosine and sine over cosine, right? So 1 over cosine and sine over cosine would give me sine over cosine squared. So I haven't actually taken the derivative. I'm just rewriting it so that I can take an antiderivative here, right? 1 over cosine, sine over cosine. And so then I'm going to go back to my knowledge of trig. 1 over cosine. What is 1 over cosine in my 6 trig functions? What is the reciprocal of cosine? Thank you. Secant, right? No, secant. Right, remember, so we have sine, cosine, and tangent, right? 1 over sine is cosecant. 1 over cosine is secant. And 1 over tangent is cotangent. If you remember it, sine was what? Your y over r. And then cosecant was r over y, right? Do you remember? Yes. Okay. Yeah. All right, so then what is sine over cosine? Tangent. There we go, tangent. So then for antiderivative purposes, you should recognize secant tangent. What gives you a derivative of secant tangent? What gives you a derivative of secant tangent? So if I had secant squared, that would be tangent. If I had negative cosecant squared, that would be cotangent. If I have secant tangent, that's secant. If I have negative cosecant cotangent, that's cosecant, right? So you have to remember you're working backwards. So the antiderivative of secant tangent is just secant. And because I do not have an initial condition, I cannot get my constant. I have to do a plus c. A plus c. One. So antiderivative of sine is negative cosine. Antiderivative of cosine is sine. There you go.